Okay. Hello, everyone. I'm Justin Essery. I'm an associate professor here at Fraser University. Welcome to the International Methods Colloquium. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Fraser University and the National Science Foundation. This week's speaker is Mark Pickup from Fraser University, with a talk entitled Transformed Likelihood Estimators for Dynamic Panel Models with Fixed Effects. Mark's talk will last about 45 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. You can ask questions at any time during the talk, but all questions will be held until the end of the presentation. A link to Mark's slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post that link right after we get started. And now I'd like to welcome Mark Pickup to the International Methods Colloquium. Mark, welcome.
Thank you very much. All right, so today I'm going to talk about estimating dynamic panel models with fixed effects when you have very few waves of data, and talk about the challenges of estimating those models, and introduce us to a transformed likelihood estimator, which is designed to overcome those challenges. So we're talking about panel data, or cross-sectional time series data, if you like. And this is the measurement of our variables of interest for the same set of n cases at multiple time points, at t time points. So your cases can be people, they can be countries, they can be firms. And panel data is quite powerful in that it allows us to identify and control for individual effects, something I'll talk about more. It also allows us to identify and control for dynamics, which I'll also talk about. Although it's powerful, when using panel data, a researcher does have to be careful to consider what model exactly they're going to use and how to estimate that model. So what estimator to use given the model they've chosen. So today's plan is to review the challenges of unobservable individual effects and of dynamics in your panel data, and discuss the challenges of estimating a dynamic model with fixed effects when t is very small. So by that, I mean 10 or fewer waves of data. So this is pretty common to those who are studying public opinion or political behavior, in that you may have a survey of a relatively large number of individuals, and you've re-interviewed them a number of times, maybe 3 times, maybe 4, but certainly no more than 10 times. And other data sets are also structured this way. So then I'm going to talk about specifically one specific transform likelihood estimator that is designed to estimate a dynamic model with fixed effects, and I'll talk about why you might want to estimate such a model. There's another transform likelihood estimator which I'll mention briefly, but due to time constraints, I'm going to focus on the one that I find performs the best. So to get us started, here's a basic data generating process for panel data. So we have here y for case I at time t, and it's a function of some covariate of interest, x, the value of x for case I at times t, plus m other possible covariates, and an error term, which we're assuming is distributed normal, zero mean, and constant variance. So today we're largely going to assume that these errors are independent of each other. I will note that we can control for some of that violation relatively easily by including time-specific effects in the model. I won't discuss that further today, except for to say that the estimator that I will be talking about performs about equally well if you include these time effects or if you don't. So unobservable individual effects. So these occur when your error is structured as such. That is, it contains a component which you'll note is not indexed by time, and that's because while the value of it may vary across your cases, it doesn't vary over time within your cases. So these are time invariant differences between cases, specifically time invariant differences that are not captured by your covariates. These are what we call unobservable individual effects. You may also know them as unobserved heterogeneity or unit heterogeneity. So these unobservable individual effects are due to a number of things, specifically characteristics of your cases that don't vary over time, or at least don't vary over time specifically during the period of your study, that is, while you're observing them. The other possibility is that they do vary over time, but during the period in which you're studying them, the values of those effects have a different average for each case. So that's functionally the same thing. So an example might be early childhood socialization. So if you're studying individuals, each of those individuals may have had different experiences when they were young. That may cause them to behave in different ways. And those differences are not going to change over the period in which you're studying your individuals. They're fixed differences. If you're studying countries, say democratic countries, there may be different democratic norms within those countries. They might change slowly, but maybe not so much during the period in which you're studying them. Or even if they are changing, the average democratic norm across each country may be different. So these unobservable individual effects have a couple of consequences if you don't account for them. So if you don't account for them, they'll result in correlation in your errors. This is because they have the same value at each time point, and if they're in the error term, then that will cause the error terms to correlate. The consequence of this is to produce an incorrect estimate of the standard errors if you use the usual formula for calculating those. So these are the standard errors on the parameters in your model, like the beta on your X term. Also, if there's autocorrelation in your covariate, so both in the error and in the covariate, like X, and T is not very large, then this serial correlation will result in biased estimates of the model parameters. So you have biased estimates and incorrect standard errors. Another consequence that may occur is that if your covariate or one of your covariates in your model itself has some time invariant component. So let's say XIT has this eta XI, so it's a time invariant component for X. Now, if that time invariant component is correlated with the time invariant component in Y, then essentially what you have is a component in the error term, the eta i's, if you're not accounting for them, that is going to correlate with one of your covariates in your model. So this sets you up for your classic omitted variable bias problem. You're violating the exogenous zero conditional mean assumption. And if you just use pooled OLS, that's just applying OLS to a model that doesn't account for those individual effects. You get an estimate, biased estimate. Okay, so that's unobservable individual effects. Next, what about dynamic data? So a dynamic process can be thought of as one where you have one or more lags of the dependent variable on the right-hand side. So here in this data generating process, we have this alpha 1 times the lag of y. This reflects the fact that y is autoregressive. What this means is that if there's a temporary shift in a covariate, whether it's in the model or not, that has a temporary effect on y, that effect will not have completely dissipated by the next observation. So for today, I'm going to assume there's just a single lag of y on the right-hand side. It's possible that there's, like say, a second or third lag. It's somewhat unusual in political science models. All I'm going to say for now is that the model, the estimators that we'll talk about today can handle additional lags of y if they're there, if you think they're appropriate. And a dynamic model also may include a lag of the independent variable, as this DGP here does. So as an example, let's say we have quarterly data. You've interviewed individuals on a quarterly basis, and we're interested in modeling the individual's approval of the government's performance as a function of their perceptions of how the economy has performed. So our theorized data generating process might be that approval is a function of the lag of approval plus perceptions of the economy, plus an error term, which say contains individual effects. So we have a dynamic model that we've proposed for the data generating process. So we would expect it to be autoregressive like that if we think that subsequent to something happening that temporarily changes approval, so for example, a temporary shift in economic evaluations, we expect approval to partly return, but not entirely return to its original value by the next time we observe it. So that means if we observe the dependent variable being above its average at one time point, we expect that it'll still be more likely than not above average at the next time point. And same thing if it was below average at the first time point. So not accounting for this autoaggressiveness in the data also has consequences. So to think about that here, let's consider that this is our data model. It's static. It doesn't include a lag dependent variable. We'll think about what happens when we estimate something like this, when the DGP is actually dynamic. It does include a lag of the dependent variable. So common estimators like pooled OLS, which I mentioned, ordinary least squares fixed effects, generalized least squares random effects, very common estimators, assume that the error term is independent of the covariates, right? That's the zero conditional mean assumption. Specifically, when t is small, it is assumed that this assumption holds such that the error is independent of all past, current, or future values of the covariates. That's strict exogeneity. So a problem arises when we're estimating this static model when this is the DGP, because if this is the DGP, then this error term is actually generated such that it includes the lag. So in other words, the lag ends up in the error term. That means the error term is a function of the lag of y, and the lag of x is also a function of a lag of y by definition here. And so the error is not independent of a lag of x. So that violates the assumption, this assumption that the errors are independent of all current, future, and past values of y. It's a function, at least in part, of a past value of x. It's a function of a past value of x. That means that pooled OLS, OLS fixed effects, and GLS random effects are going to be biased for the estimate of our beta 1 here. So that's obviously a problem. Another problem is that the errors will be serially correlated. Probably the easiest way to think about this is that the errors contain this lag of y, and just like y, the lag of y is autoregressive, so your errors are going to be autoregressive. When estimating a static model, if you see that your errors are serially correlated, one might be tempted to use something like a feasible generalized least squares estimate, such as Price-Winston or Cochran-Orcott, to account for the serial correlation. The problem in this situation, and this is a situation where the DGP contains the lag of the dependent variable, is that this correction for the serial correlation will not correct the bias caused by the violation of the zero conditional mean assumption, or and the serial correlation. The zero conditional mean assumption. Okay, there's also in this case going to be a problem of inference, and that's because in a dynamic process like this, the long-run effect of a covariate like x and the short-run effect are different. The short-run effect here is beta 1, and the long-run effect is going to be beta 1 divided by 1 minus alpha 1. Right? So there's differences, but in a static setup, beta 1 is the immediate and only effect. So not only in this situation would you get a biased estimate of beta 1, we'd misunderstand exactly what the dynamics are between x and y. A similar problem of inference can occur if you've excluded a lag of x from the model. So if it was in the DGP and you excluded it from the data model, you'd have a problem of inference there as well. And you get a biased estimate as well. Okay, so what we've done now is look at problems for not accounting for unobservable individual effects, and problems when you admit a lag-dependent variable when it's in the data generating process. I'm just going to note that we can account for both by estimating a model like this, one that includes a lag of the dependent variable, one that includes one or more lags of the independent variable, and explicitly models those individual effects. Now, I do want to stress this is not a panacea. That is, this is not like you should just always estimate this model. That's not what I'm saying. Certainly, there are data generating processes for which this would be inappropriate. But today, what I want to focus on is the estimation of a model like this rather than the specification, although that's a very important topic. Today, I want to talk about how one would estimate such a model, and one would want to if one believed the data, in fact, was autoregressive, first order autoregressive, so contains the first lag of y and contains these unobservable individual effects. Okay, so what are the challenges with estimating such a model? Well, the two most common estimators used to do this, to account for unobservable effects anyways, are OLS fixed effects and GLS random effects. Now, GLS random effects assumes, as most of you probably know, that those individual effects are independent of all the covariates. The problem is that in a dynamic model, this assumption just can't be met. And that's because by definition, the individual effects cannot be independent of y, right? So y is a function of the individual effects, so the lag of y also are a function of the exact same individual effects. So there is by definition, a relationship between this covariate and the individual effects. So the assumption necessary for GLS cannot be met, and so it will be biased. It's been shown that it is biased towards what you'd get from an OLS pooled estimator. That is a model which ignored this term. And you also get incorrect standard errors. They'll be they'll be incorrect. With OLS fixed effects, with a dynamic model, when t is small specifically, you get what's known as nickel bias. And an intuitive way of maybe thinking about that is that events that occur that affect y just prior to your first observation will not have fully dissipated before the last observation. And this is because of the small number of time periods in which you're observing it. This lack of dissipation will appear similar to a fixed difference between the observations, making it hard to distinguish between a fixed difference and simply the autoregressive nature of the data. And so that makes it hard to estimate those two elements of your model. And it's been shown that if the autoregressive parameter in the DGP, alpha 1, is positive, then the bias will be negative. So you're going to get a downward bias on that parameter, and this has a knock-on effect of biasing the other parameters in your model. Okay, so these are known problems. So a common solution is to use a generalized methods of moments estimator, say as the one as spelled out by Arellano and Bond in 1991. So there are a number of different GMM estimators for dynamic models with fixed effects, but they generally all begin with what's called a first difference transformation. So let's see what that is. So if we assume the DGP is as follows, right? Y is a function of the lag of Y, you have X and the lag of X and these fixed effects, then the following is also true. I've just lagged each of the variables. So if this is true, then this is true. So if we subtract 7 from 6, then what happens is, because these terms are exactly the same, because they don't vary over time, they cancel out. So we now have a model that doesn't contain those individual effects, and it's now in first differences. Oops, that's disappeared. So we have here the first difference of y minus the lag of y. That's known as the first difference of y. Here we have the first difference of the lag of y, first difference of x, first difference of the lag of x, and although it's disappeared, this is the first difference of the error term. So we use delta to represent the first differences. The problem with estimating just this is that by definition of our original DGP, this error term, the first difference of the error, is not independent of the first difference of the lag of y. This is because that first difference contains the error term, which is contains the lag of the error term, which is missing here, which is a function of the lag of y. So in order to estimate this, Anderson and Chow proposed that we could use an instrumental variables solution. So they suggested either using the second lag of the first difference, or the second lag of the level of y as an instrument for this term here, the one that's endogenous to this. And that works fairly well, but it has a lot of limitations. So Arellano and Bond in 91 proposed a generalized methods of moments estimator version of this approach. So in the GMM estimator, the instruments define moment conditions, and GMM proceeds by selecting values for the parameters, right? So the betas and the alphas, selects the parameters that minimizes a weighted sum of these squared moment conditions. Now, I don't want to spend a lot of time describing GMM because I want to spend more time describing the transform likelihood estimators that are not well known, because GMM estimators are well known both within and outside of political science. So I will say, though, because this is important, that this approach requires a weighting matrix for that weighted sum of squared moment conditions. And as we'll see, this can be difficult to estimate, and that's going to cause problems for GMM. Now, the advantage of Arellano and Bond over Anderson and Chow is that it allows for a greater number of instrumental variables. So in other words, allows for more moment conditions, and as a consequence, it performs better. The number of moment conditions, though, is determined by the number of waves of data. So the more waves you have, the more moment conditions you have, and generally up to a certain point, Arellano and Bond GMM estimators will perform better. It can perform poorly, though, if the autoregressive parameter, that's alpha 1, is close to 1. Or the variance between cases is large relative to the variance within cases. So an extension of this estimator was proposed. It's a system GMM, which says that you can find moment conditions not just in the first difference equation, but also in the original levels equation. That gives you additional moment conditions, which then allows the estimator to perform better. So this addresses some of the shortcomings of the Arellano and Bond 1991 version. but it has some drawbacks. So one drawback is that the optimal weighting matrix can be difficult to estimate when you have limited information. And this occurs when your moments are based on weak instruments. So this is the equivalent of the weak instrument problem, or when the number of moment conditions is large relative to your number of cases. So this would be the many instruments problem. So when you have those, this can cause problems with estimating the weighting matrix. Now, that difficulty doesn't necessarily produce bias in your estimates, but it does reduce efficiency. So in other words, it results in larger standard errors, and that obviously is a problem if you're engaging in inference, if you want to test a null hypothesis, whether a coefficient is equal to 0 or not. Further, the many instruments and weak instrument problems on their own, other than creating problems in estimating the weighting matrix, they can on their own result in bias. And this bias will be in the direction of the OLS fixed effects estimator. So this one suffers from nickel bias, and GMM, when it has a many instrument or weak instrument problem, will be biased in the direction of that estimator. Finally, GMMs are efficient to the extent that the available moments can be identified by the researcher and used. It's been noted that as applied to dynamic panel models with fixed effects, it tends to be inefficient. So again, resulting in larger standard errors. So just to get a sense of how these traditional estimators perform, let's run some Monte Carlos where we'll generate some data sets with a data generating process that we know, and then apply these estimators to them and see how they perform. So we're going to use a DGP where it's dynamic, includes a single covariate, and includes individual effects. The covariate X is itself a function of the same individual effects, and the errors are just going to be well-behaved, normally distributed errors. So this has the problem of dynamics and the problem of individual effects that we would want to account for in a model. We're going to use beta of 0.5. We're going to generate data sets where the alpha 1 is 0.9. These estimators have some of the worst problems when they're close, alpha 1 is close to 1. So we'll look at that. We'll also reduce alpha 1 to 0.5. So we'll see what happens when alpha 1 is less problematic. The individual effects are just generated from a uniform distribution. Okay. We're going to look at panel data sets where t is equal to 2 and 9. When I say t is equal to 2, we mean we have 3 waves of data, but we lose the first wave because it supplies the lag of the dependent variable for at t is equal to 2 at the second time point. And then we'll have n of 1,000, meaning that we have a large n, and we'll reduce that later on. Okay. And for each combination of t and n and alpha, we're going to generate 1,000 data sets and apply the estimators to see how, on average, how well they do. So this first row provides the results for alpha, beta, and the estimated long-run effect, which is important with dynamic models. The point gives us the bias. The farther it is from the 0 line, the more bias. The bars give us plus or minus 1.96 times the root mean squared error, except for here. For the long run effect, I've actually used the 95 percentiles for the distribution of the estimates. That's because the long run effect is a nonlinear combination of these estimated parameters. So there's no particular reason to believe that the distribution of the values are going to be symmetric. So it's more useful to do something that allows for that non-symmetry. The bottom row demonstrates the coverage and the power. The coverage is the proportion of times that the 95% calculated 95% confidence interval includes the true value. So ideally it would be 0.95. And the power is the proportion of times that the 95% confidence interval excludes 0. So ideally it would be 1. So first we're starting with t is equal to 2. We have 2 waves of data and alpha is 0.9. And we see that pooled OLS and GLS random effects have some bias for alpha, not too bad for beta, and a large bias of the calculation of the long run effect. It has root mean squared errors that are not small, but not large. Note that they actually look very similar, and that's not surprising because we know that GLS random effects, when you violate the assumption necessary for it, will be biased in the direction of the pooled estimator. So that occurs when you're estimating a dynamic model with GLS random effects. OLS fixed effects, we see the expected downward bias, large downward bias on the alpha term, and that has a knock-on effect of a downward bias on beta and the long-run effect, and it has very large errors. GMM here has very large errors. We would expect the large errors. It's also biased, which is not necessarily expected, except what's happening here is that with only 2 ways of data and very limited information in terms of those moment conditions, the estimator is having troubles estimating that weighting matrix. And in fact, the command I used to estimate this actually gave that warning, that it had troubles estimating the weighting matrix. Note also that pretty much all of the estimators have pretty poor coverage, GMM being the exception. And that means that essentially the confidence intervals are so underestimated that they're too small and they're not including the true value. So these estimators clearly have some problems. If we increase t to 9, we note that the bias for the GLS random effects doesn't really change. The root mean squared errors get, well, a tiny bit smaller, but not really. OLS fixed effects is beginning to get less problematic, although even at t of 9, which is quite a large t in some instances, is still biased. And now GMM, you note, is no longer biased, although its errors are still fairly large. And you note that except for GMM, the coverage is still pretty poor for these estimators. So not very good for inference. Now, if we go back to t is equal to 2, but reduce alpha to 0.5, so this could be less problematic for these estimators, but note, it's not. That the estimators generally all have the same problems they had when you had alpha is equal to 0.9 and t is equal to 2. So t is equal to 2 is really a problem for these estimators. And admittedly, is not a lot of data, but even at t is equal to 3 and all the way up to 9, you see similar problems. Okay, so those are the estimators we're familiar with. Let's consider likelihood-based estimators. So traditional MLE has a problem when estimating a model like this. That is a model with fixed effects and that is dynamic. Right? It leads to an incidental parameters problem. So MLE, when t is fixed at a small value, requires, in order to be consistent, that n is large and is large relative to the number of parameters being estimated. In other words, as n increases, it has to increase faster than the number of parameters that you're going to estimate. The difficulty is that when you have fixed effects, the number of parameters approaches infinity at the same rate as n does. That is because every time you add a case, you increase n, you're adding a parameter you have to estimate. So we can't therefore rely on asymptotics in n, and so the application of MLE, just basic MLE, will lead to an inconsistent estimate of this model. So the key to the approach I'll talk about today, which I refer to as orthogonal reparameterization, is that we're not actually interested in estimating those individual effects. They are incidental parameters, right? And so this is an approach that was proposed by Lancaster. Now, 2002, that's a while ago, so this doesn't seem like a new estimator. However, it's not used in political science, and actually it's very rarely used anywhere. So it's essentially new to us. In fact, it's new to almost everyone. I refer to it as OPM simply because I don't want to say orthogonal reparameterization over and over again. So what we're interested in is not these terms, but what we call the common parameters. So in our previous model, what we're interested in is alpha 1, beta 2, and the variance of the error term. So not the incidental parameters. So this approach proceeds by seeking a reparameterization of these incidental parameters so that these incidental parameters and these common parameters are information orthogonal. So that's a bit of a mouthful. That requires us to understand what reparameterization is and what information orthogonality is. So to understand the concept of reparameterization, consider this example. So let's say we have, this is just a basic static model. Y is a function maybe of an intercept, beta naught, beta 1x, the incidental parameters plus an error term. Okay, so we can define a new set of parameters, which we're going to call eta tilde, as a function of the original parameters plus beta naught. So this is how we're defining these new incidental parameters. And if you apply that to our original model, then our model looks now like this, right? So this is just this is a reparameterization of those incidental parameters. And note that this reparameterization hasn't changed the parameter of interest, beta 1, or the variance of the error term, right? So it's changed the meaning of this term, right? But it hasn't changed these two. So the orthogonal reparameterization proposed by Lancaster is quite a bit more complex than this. But just like this example, it changes the meaning of the incidental parameters, that is the parameters representing the individual effects, but not the meaning of the other parameters, the ones that we're actually interested in. Unlike this example, though, the Lancaster reparameterization also allows us to write a likelihood in which the incidental parameters are informationally orthogonal from the other parameters. So what does information orthogonality look like? Okay, so suppose we have a likelihood with the original incidental parameters and the common parameters. And let's say that we can come up with a reparameterization of those incidental parameters so that when you do that, the likelihood can be factored into two, so that this likelihood could be written as the product of two likelihoods. These are both likelihoods, and the first is a function only of those new incidental parameters, and the second is a function only of the common parameters. So this, along with information invariance for the parameters, is shown that you can take this likelihood, just this part, and apply maximum likelihood to it, and that will produce consistent estimates of those parameters of interest as n goes to infinity. So we never get estimates of these parameters, but we're not interested in them anyways, so we're okay. So as an example, a simple example, consider a Poisson count model with fixed effects. It's a relatively simple model, so it's a nice example. So here's a likelihood for an individual I. We can reparameterize so it's a function of the original of these incidental parameters plus the common parameter theta. So we can reparameterize these by defining the new parameters as a function of the original incidental parameters and the common parameter. That produces a new likelihood, which looks like this. Right, so there it is. So this is a product of two likelihoods. The first is a function only of those new incidental parameters, and the second is a function only of the common parameters. Right, so we can maximize this to get an unbiased estimate of theta as n goes to infinity. Now, not all likelihoods can be transformed so that they're completely orthogonal. Right? So in this case, the incidental parameters and the common parameters are completely orthogonal. It's not always possible to find a transformation so that actually occurs, but we may still be able to find a reparameterization of those individual effects so that they are information orthogonal from the common parameters. So what does that mean? So if the incidental parameters are completely orthogonal, as they were in the Poisson count model example, then what we're saying is the derivative of the log likelihood with respect to those incidental parameters and the common parameters is 0. And we may not be able to get this, that is complete orthogonality, but we may be able to get a weaker form of orthogonality, in which the case this will be true in expectations. So there we have, in expectations, the derivative of the log likelihood with respect to the transformed incidental parameters and the common parameters is equal to 0. So intuitively, we can think of this as meaning that the slope of that log likelihood here, with respect to the incidental parameters, is independent of the slope of that likelihood with respect to the common parameters, which means we can maximize with respect to the common parameters without worrying about what the values of the incidental parameters are. Without orthogonality, we can't do that. So that means we don't really need to worry about what the values are for the incidental parameters. Less informally, what we're saying is that these transformed individual effects are orthogonal to the common parameters if the component of the expected Fisher information matrix that correspond to the A to I 0 are 0. So if these components are 0 in this information matrix, then we have information orthogonality, in expectations. But it's best probably to think about it in a more intuitive way. So if you can find with a transformation of the fixed effects, that is the incidental parameters, that meets this condition, then what we are is in a position to place priors on all the parameters and integrate out the fixed effects. This will give us a marginal posterior for all the remaining parameters. That is the parameters we're interested in, and that posterior will not contain the incidental parameters. If we have that, we can use Monte Carlo methods to sample values from that posterior, and I won't go into the mechanics of that, but the end of these notes, so the end of these slides do contain some notes on how that works in practice. Once you've sampled those values from the posterior, the medians of the sample values for each of the parameters gives us our parameter estimates, and the 2.5 and 97.5 percentiles give us our 95% credible intervals. So, as you probably could tell, this is essentially a Bayesian estimation technique. Now, I'll note we didn't have to reparameterize to do this. That is, without reparameterization, we can place priors on the parameters and integrate out the fixed effects, the incidental parameters. But what the orthogonalization gives us is that it means that the choice of prior doesn't matter. The choice of prior on the individual effects do not matter, right? And otherwise, it would. And so that could lead to a question as what is the appropriate prior? So the orthogonalization means we don't need to worry about what prior we place on the fixed effects. And so this orthogonalization then provides a consistent estimate of the parameters of interest as n goes to infinity. So this can be done in a package that's our package called OrthoPanels, and there's an R journal paper that describes the mechanics of that package. I should note that there's one other estimator that's of interest, and that's the proposed by Anderson and Chow. It's likelihood-based as well. It's available in a Stata package. It's often referred to as a quasi-maximum likelihood estimator. It also transforms the likelihood to remove incidental parameters, but it's more frequentist in nature. And while it performs very well compared to traditional estimators, it generally doesn't perform quite as well as OPM, so that's what I'm going to focus on. To see how well OPM performs, let's perform the same Monte Carlo simulations as before, but now we're going to look at how OPM performs. So this is what we had, same simulations as we had before. T is equal to 2 and alpha is equal to 0.9. And these commonly used estimators, we've already seen their problems under these circumstances. We see that OPM is unbiased, has relatively good errors, except for here, which I'll talk about in a moment. It has good coverage, actually has great coverage, and power. So it works very well. It only has this problem in that the errors for the long-run effect are not small. This turns out to be a problem for pretty much all estimators. And this is because alpha is close to 0.9. So because the long-run effect is estimated as beta divided by 1 minus 0.9, small errors in the direction of 1 produce large errors in the long-run effect because of that division by 1 minus something close to 1. So all estimators struggle, but when t is equal to 2 at least, and alpha is equal to 0.9. But as we see that OPM is certainly much better than the estimators that are traditionally used. When we allow t to go to 4, we see that OPM performs extremely well. Right, so very small errors, unbiased, great coverage. The other estimators continue to have problems, although GMM is no longer biased, or mostly not biased, but it does have large errors, which causes some problems with actually its coverage is still pretty good. But it has these large errors. So that's what we traditionally know about GMM, is these large errors that it causes. So let's go back to t is equal to 2, but alpha is equal to 0.5. Again, we see that OPM performs extremely well. Great coverage, not biased, small errors. Because we're back to t is equal to 2, GMM is back to the problems that it has in terms of estimating that weighting matrix, causing not just large errors, but also bias. And OLS and GLS are also having their usual traditional problems. Now, the properties of these estimators are usually derived with a large n. And now we know in most or many political science examples, n is not always large. So what happens if we reduce n to 500? So again, t is 2, alpha is equal to 0.5. We see that OPM performs again very well, good coverage, small bias, reasonable errors. Again, though, as all estimators run into, is that it has this problem when t is only 2 and alpha is close to 0.9 in terms of the error on the long run effect. But still, again, a much better performance than all of the other estimators. let's reduce n to 40, but let's increase t to 4, because most political scientists that use a small n, they do realize they need to get power from somewhere, so they usually choose a data set with a larger t. And we see that, again, OPM performs quite well, same as, basically it performs as, slightly larger errors, but it performs basically as well as it has in the past. We begin to see at this point a little bias in there, but very small. And the other estimators, again, have their traditional problems. Either they have bias, poor coverage, or large errors. Now here's t of 2 and n of 40, and this is a situation I would not recommend anyone actually estimating a model under. But what happens? Well, again, all the estimators generally begin to run into the problems. OPM is still clearly the best estimator. A little bias, again, is creeping in, but the coverage is actually quite good, and the errors are large, but they're smaller than most of the estimators. And it's certainly the only one that's unbiased. So likelihood-based estimators have built into them distributional assumptions. And so one of the questions might be, well, how would a likelihood-based estimator perform if those assumptions are violated? So let's consider 3 common violations of distributional assumptions. The first is outliers. So I want to look only at GMM and OPM here. We know the other estimators are not perform very poorly. And here, for these first 2 estimates, these DGPs have y distributed t 10 degrees of freedom. So it has the fat tails you expect that would be produced by outliers. And the second 2 also have an x distributed t of 4. And what we see is that for alpha, the GMM is unbiased mostly, but has large errors. And for beta, it's biased. OPM, unbiased in both cases with reasonably small errors. And OPM also has reasonable coverage under those circumstances. We're going to consider skewed distributions. So here, the first 2, y is distributed beta 2,9. It's quite skewed. And in the second 2, we also allow x to be distributed beta 2,5. And what we see is GM is either has large errors or is also biased. While you see OPM, these 2, are unbiased and have very small or reasonable errors and have decent coverage. So it's performing fairly well. Finally, a bimodal distribution. So the first 2, the y is distributed beta 0.9, and then the second 2, we allow x to also be distributed beta 0.5. And so again, GMM runs into its problems, large errors and even bias. And we see that OPM is unbiased in all cases and has very small or very reasonable errors. So overall, even though likelihood-based estimators do make distributional assumptions, the OPM is quite robust to common violations of those distributional assumptions. So to summarize, we've discussed the challenges of dynamic data and individual effects and estimating models that account for those when t is very small. And we've discussed one particular likelihood-based estimator, the orthogonal reprioritization estimator, for models like this, which performs very well under almost all conditions and certainly performs better than the estimators that we traditionally see being used in political science today. And that's where I will stop. Thank you.
Okay. Mark, thank you for that presentation. At this point, Mark Pickup is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And we actually have a question. I was going to ask a question, but I always give deference to the audience when I can. So an anonymous attendee asks, I have a question regarding possible heterogeneity in alpha for dynamic panel models with fixed effects, i.e. different dynamic structures for different cross-sections. Could be different numbers of lags of y or different alpha values. This could be accounted for by using mixed effects models under MLE. We assume during the DGP that all cross-sections share a common. I assume that a common alpha is what they mean there. But is there a way to account for this when we reparameterize incidental parameters? Because different dynamic structure could also lead to biased estimate of our betas.
Yeah, no, that's a good point. It is a limitation of pretty much all approaches. So even the approach suggested by the questioner, it will run into problem when t is small and you have a dynamic model. So there's actually to date no actual solution to that problem when t is small. Now, when t is larger, there are ways of accounting for that problem. All sort of solutions to that type of heterogeneity largely require a relatively large t because it is some version of estimating separate models for the different cases. Maybe not entirely, maybe it's pooling over those, but there's some separation of the model for the different cases. And of course, when t is small, you really can't do that. So that's kind of where the limitation is. And it's not just for the orthogonal reparametrization approach. Pretty much all estimators, when you have a very small t and you estimating a dynamic model with fixed effects, will run into that limitation. But it is important to recognize that that is a limitation at this point in time in our technology.
I wanted to ask a question about the sort of, I guess this is really about overall these GMM instrument estimators. This is a sort of a member of that family. My experience has been that the Ariano bond and Blundell bond kind of GMM estimators eat results. And in other words, something that looks pretty good in a random effects model or a pooled model or whatever just gets destroyed by an Ariano bond model. And usually the sign doesn't change too much, but the efficiency goes way, way down. And so this is sort of a two-part question. The first part is just about strict efficiency properties. I noticed the power seemed a little bit better in this model compared to those models. I was hoping you could talk about that a little more. And then the second part of the question is really about between effects versus within effects, right? So this is a within effects model, if I understand it correctly. Mm-hmm. And sometimes we think that between effects are pretty important too. They're not all ascribable to unmodeled unit heterogeneity. And I'm kind of wondering, if, from a practical perspective, if someone's going to try to analyze this data and they think between effects are kind of important, how this model sort of speaks to them, or what other opportunities, what other things they can do to recover that part of the variation in their data.
Yeah, so the first part was about GMM and its efficiency. So that is a classic problem. So GMM in itself, the broad approach, can be efficient. Right. It's not probably GMM. It's the way it's being applied here. Yeah. And no, it's true. And this is one of the things this resolves, is that it has much better power, and it just basically produces smaller standard errors. So you're not going to have that problem where the effect disappears, at least not because of the standard errors. Now, GLS, if you're using a dynamic model with fixed effects and a very small t, then GLS and OLS are biased. So if the effect goes away, well, that may be just because the original effects were biased. But this will not. So, or at least the OPM and the other likelihood-based estimator, which I didn't really have a chance to talk about, will produce unbiased effects and will be much more efficient. So they're preferable over any of the other approaches. The between estimate, so when this is a within estimator for sure. When I usually describe these model, I indicate that this is for people interested in the within effect. If you're interested in a between effect, then you wouldn't want to use this model, this estimator, sorry. But the problem is, it's not clear what estimator you could use when t is small, because to get a between estimator, you're having to make assumptions which aren't going to be met when you have a dynamic model and t is very small. If you're outside of the world of dynamic models, you're okay, you're great, right? And a lot has been written about models that are not dynamic, and all's good there. And there's a lot of advice in political science already on that, and so I won't go into detail on that. The problem is that when you have a dynamic model and t is very small. Now, if t is larger, right, you have a very big t, then you can actually use OLS fixed effects, or you can use you can find there is a random effects estimator, not GLS random effects. That's still going to be biased, but there is a likelihood-based random effects estimator that you could use. And that random effects estimator then does allow you to estimate both between and within effects under certain assumptions that they're the same. So, and actually, I would say that estimator is also a quasi-maximum likelihood estimator. And if people are interested, I could post what that estimator is. It actually does work, now I think about it, when t is small. So I would say that if you think you can make some necessary assumptions, you can use that random effects estimator for a dynamic model when t is small. So that would actually probably be your best choice, but you are going to have to make some fairly strong assumptions for that to work. I've begun to explore the performance of that estimator, and it works quite well, except for when alpha is very close to 1, and it begins to run into problems there. But I will post, if you like, somewhere what that estimator is in the background on it. It is available in a Stata package, so that might be of interest to some people.
Yeah, when alpha is close to 1, you have an almost explosive series, right? You're close to a random walk. No, you're close to a random walk anyway, right? So that's probably.
And so two things though, yeah. When t is very small, obviously, so when it's close to 1, the effects of a temporary change in an x will dissipate very slowly, and because you're not looking at the time series for very long, you don't get to see the dissipation very clearly, and that makes estimation of the models a lot harder.
Mm-hmm. So in terms of, I saw that you have an R package. I was looking at the documentation for your R package. In terms of those people who may be watching, thinking about sort of substantively when when it would be appropriate to apply this model as opposed to some other approach, maybe a between effects approach or something else. I know you mentioned, when you have long T, obviously OLS FE is probably fine. What are the sort of substantive problems that you think this model is going to be most applicable to? I know I'm asking you a bit of a loaded question here, like describe all political science. But what did you have in mind when you were developing this estimator?
Yeah, so a lot of my work is in political behavior, and so I became aware of this model and decided to program it up so it could be used for that type of work, where you have maybe 3 or 4 waves of survey data, and often it's not unusual in survey data, like when you're measuring individuals' behavior, that you expect it to be autoaggressive, and you often certainly expect there to be differences between individuals, say due to socialization or other reasons, that we expect to be fixed, at least during the period in which we're studying them. So it could be election data, but it doesn't have to be. We also have other longitudinal data where we interview individuals over time, but we almost never have a large T for that type of data. I mean, large for those type of data is 10. I mean, that's the biggest you're going to see. And so you can see even with a T of 10, the estimators that most people are using are problematic. So this is when I would suggest using this estimator. As I said, if you can make some fairly brave assumptions, there is this other random effects estimator, also likelihood-based, that I would recommend. I would say, note something actually, because you mentioned earlier the R-Lano and bond. I would say the other challenge of R-Lano and bond is that the researcher has to choose what moment conditions to use. And as T gets bigger, there's more and more options. And it turns out often you can produce big differences depending on which moment conditions you use. That is, in my mind, too many researcher degrees of freedom, right? I mean, ideally, you wouldn't do this, but you know that researchers are going to find different results from different moment conditions and choose the one they like. And that's really problematic.
How many lags of should you use as instruments? This is a problem I actually spent a lot of time working on for a recent paper, and it's hard to choose without basically p-hacking.
Exactly. The advantage of the likelihood-based estimator, and you'll see this in the ortho panels package, there isn't a lot of options there, partly because we're still developing it. But one of the reasons there aren't a lot of options is because you just don't have those options here. Right? There's no question of what instruments should you use. And so you really can't engage in that type of p-hacking with this estimator.
I have one last question. So there's a paper by Clark and Linzer, very, very intelligently named, I thought, very, very SEO, called "Should I Use Fixed Effects or Random Effects?" And this sort of encapsulates a whole debate between basically econometricians who are very high on fixed effects and the various advantages that those models have, and then sort of Gelman and Drew Linzer and a bunch of sort of more statistically, or I think more statistics department-oriented people who essentially argue that REs are they're biased, but they're also much lower variance. And so the overall RMSE trade-off is better for the random effects models. That's the crux of the argument. And I'm wondering I was looking at your simulations there. I'm wondering if this approach sort of changes that recommendation at all.
It changes it when your data is dynamic, or you believe it's dynamic, and you're including a lag-dependent variable. That debate is largely, that paper specifically you mentioned, is for static models. And so that most of the debate in political science over that has actually been either when the data, you're using a static model, in which case the results, I agree with them, or you have a very large T, in which you got a different scenario again. So this changes that debate if you're going to use a dynamic model, and they don't actually address that. So that's why I'm not saying they're wrong. They just aren't doing a dynamic model. Where I will disagree with them a tiny bit is that they're looking only at the trade-off for the root mean squared errors. They're not looking at coverage. And I think, and I'm doing this now with some others, when you replicate their simulations, but you look at the coverage, it isn't as clear that the random effects, the trade-off for the random effects is as good as you think it is. There actually are real problems with coverage. And of course, coverage matters because it tells us it's important for whether or not we're correctly testing the null hypothesis. And if you're incorrectly testing that, usually we care about inference. So I would say that replicating what they have with also looking at coverage will somewhat nuance that finding.
I feel like I know what Drew would say to that, which is he doesn't care about null hypothesis testing.
Right. And that's fair enough for him. And he wrote the paper he wrote, and I don't disagree with what he concluded in the bounds of what he wrote.
Yeah, no, I think that's a good way of putting it. Well, we are basically out of time, so there are a couple more questions. I'll make sure to pass those on to Mark directly. But I want to thank Mark for giving the presentation this week. His presentation will be posted to our website a little later today if you'd like to share this broadcast with someone else or watch it again later. I also want to announce a talk next week. So Friday, March 2nd, we will host a talk from Eric Peterson of Dartmouth University. His talk is entitled Demand Effects in Survey Experiments and Empirical Assessment. Please visit our website, www.methods-colloquium.com, to get more information about this talk. Mark, thanks for giving the talk this week.
Thank you.
Yep, and see everyone next time.